Hey guys, so today we're going to be doing a friction lab. This is actually a two-part lab. So some things you'll need for this activity, this is part of our STC kits here at school. You're going to be using your demonstration table in front of you, a heavy grit, what we call brown grit paper, some parchment paper, like what you could use to cook with, or sometimes it's called wax paper, and then a lighter grit or less grit wax paper. No, sorry, grit paper. My apologies. Also, you'll need a rubber band. You'll need this wooden block to represent an object being moved. It does have a hook in it, so be careful. Also, you're going to have a spring scale. The spring scale you might have seen in a grocery mart, produce store, etc. Usually they're a lot larger, hanging up, so you can weigh your food. So this can either be used to measure pounds, or what we're going to use it for is newtons, because we've been talking about forces. Remember, a force is a push or pull. Then we've also kind of extended with that, talking about balanced and unbalanced forces. Remember, a balanced force is just like this wooden block on the table. It's not moving. Our net force is 0. Or if it's an unbalanced force, the block will move, and that would show that it had some value for the net force. Remember, your net force is always a positive value, and our unit is newtons, after that cool dude, Sir Isaac Newton. So to do this lab, remember, we're applying friction. So friction, what in the world is this crazy thing? A lot of times we say in class, put your hands together. So two opposing forces has to come together to create contact. And if you rub, it creates heat. So that tension or friction resistance is friction, which is kind of cool. So we're going to figure out how friction is beneficial, also how it applies to different surfaces, and what does that mean. So I'm going to start off with the block on the table, just the table by itself. Usually you want to have at least 2 or 3 different types of mediums or surfaces to try to do a lab. Also, we're going to do 3 trials. The reason why you want to do more than one, because that's more data. So your scientific observations are going to be more pliable than if you just did one trial. Because always we do trial and error. So for this first one, we're not going to use the rubber band, so set that to the side. We're also laying the block flat on the table. You'll see why here in a little bit. So you're going to attach your spring scale to your wooden block. Actually, I'm going to hook the hooks together. Now, when you're pulling the block across the table, you don't want the spring scale to be tilted. You want to kind of lay it flush on the table. And as you pull gently in a constant motion, the little red indicator is going to come downward, showing you the maximum amount of newtons being pulled. So I'm going to hook my spring scale to my wooden block hook, and then I'm going to pull it across the table. And yes, it's going to. I do have some tape down to show like kind of the same distance. For that one, I got 0.5 newtons. Yes, you can get decimals. I know sometimes that's not our friends, but we got to use them, y'all. So if I do it again, I got 0.5. And the third time, I got 0.5 as well. So a way that we can compare this a lot easier than having so many different values is we take the average of our 3 trials. So for the table, I would do 0.5 each time. So when you add that up, you get 1.5. And in order to do your average, that's the same thing as our math people would say mean, and you divide by the number of trials. So 1.5 divided by 3 is 0.5 newtons. You got to include those units, y'all. Otherwise, it doesn't count. So for the table, we got 0.5 newtons. Now, your data could have been different than mine, but on average, we're looking at less than a newton for the table. We're going to do the same thing with the brown wax paper, brown grit paper, the wax paper, and then the lighter tan grit paper. I'm going to show you with the values on the screen my findings. Again, everybody could be a little different, but it should be in a certain amount of ranges. So that's when we have a flat load, pretty much. Let's say this is just a truck. Well, what if we stepped it up a notch and made it a tractor trailer or a larger vehicle? Well, we could change our load, okay? So this is where the rubber band comes into play. So this is like part 2. We can demonstrate the load change being like at the bottom. So instead of being pulled by the hook, we're going to pull by the rubber band. So again, these blocks are very fragile. Yes, they're wood, but things can happen. So if you're doing this experiment in class, kind of cup your hand over the wood so that it's not going to fall over. So we can change the load this way as option 1, or you can change the load to be a little bit different, like top heavy. Make sure you cup your hand to guide it as you're pulling, because we all know things can happen in the lab room, but safety first. So I'm going to choose to do my load this way. So I put the rubber band toward the bottom of my block. Instead of attaching it to the hook at the top, I'm going to attach it by the rubber band. And yes, sometimes it takes a little bit of practice. Okay, so now I have my setup. I'm going to do the table one more time. So as I'm pulling, this one is actually going to like 0.6. Try it again 3 times, remember? So this is the second time. 0.6. 0.6. So again, this one had to have a little bit more force applied in order to pull the block because we changed how the load was. So a lot of times when you're moving, you got to be careful how you box things because that can influence how you travel. Okay, so again, also this interferes with car design. Do you want a sleeker car or more of a boxier car to go with air resistance? But again, I changed my load to be this way, so it's a little bit more top heavy. So that had 0.1 newtons more, so 1/10 more newtons to pull that block. Crazy. And I'll put the data on the screen of when I did the brown paper, the wax paper, and the tannish lighter color grit paper. So questions we want to kind of observe. What required the greatest force? So what type of surface required the most force or had the most newtons? And which surface had the least? Also, how did the position of the block influence the force? Well, we already know that if you change the position, you had to apply more. In some cases, it might be some different data, you might need less. Also, if we were in class, you would graph your data so we had a visual. And I'll show you what my graphs look like of the different averages along with the different surfaces. All right, y'all, so that is friction. So again, ways that friction was applied with balanced and unbalanced forces. When your block is on the table just resting, that's a balanced force. When we moved it with the spring scale, that would have been an unbalanced force. Ways that friction is beneficial to us, gravity is what pulls us toward Earth. Friction allows us to walk on Earth, so our feet have resistance to the surface. Like I was saying earlier, if you have like different types of weather in the wintertime and it's icy, your tires are going to be all over the road if you don't have good tread on your tires. And a lot of times you might see brine on the roads, like salt. They put that on the road so your cars can have friction on the roads so we can get safely to where we're going. So friction can also be beneficial to try to cut friction. Swimmers wear swimmers caps. You might have seen in the Olympics, they wear the caps so that their hair is not everywhere because that can actually slow you down when you're swimming. Or bikers, they wear like a more aerodynamic helmet, or they wear like a bodysuit when they're biking, doing the Tour de France even. So there's different ways friction can be applied. It can be helpful. It can also be hard too. Like maybe if you're trying to apply brakes to cause that friction to slow down and your brakes give out, that could be a bad thing. So there's different ways friction impacts us in this world. Hope you enjoyed, and if you have any questions, please contact your teacher. Have a great day.